the first announcement of note is on Monday there will be a quiz. It'll be an individual quiz. It'll be mainly multiple choice.
Can there be a lecture?
No, Monday will just be quiz.
Okay.
Yeah. With the idea that the quiz will be written so that it will be comfortable to complete in one class session. So so the last thing that I want to introduce is just one final topic, mainly inspired by properties of quadratic functions. So here's a quadratic equation. X squared plus 2x plus 2 is equal to 0. What are the solutions to that equation? Well, I guess maybe better is let's just talk through, let's solve that equation. What technique would people rather see? The completing the square technique or quadratic formula? Quadratic formula? Completing the square? Okay, I'll complete the square. Since this is an easy thing to apply it to, it's got leading coefficient 1, and that's even. That x plus 2 tells me that there should be an x plus 1 quantity squared showing up. Because then when you FOIL that out, you get x squared plus 2x plus 1. I need x squared plus 2x plus 2, so I'm off by 1. Add an extra 1. So instead of solving that equal to 0, I can set x squared plus x plus 1 quantity squared plus 1 equals 0, and I can solve that now just manually. Subtract 1 to the other side. X plus 1 squared equals negative 1. Does anyone notice any problems about that? Yeah. What's the problem? Yeah. Squaring something and getting a negative. Can squares ever be negative? Not in the sense of real numbers. If you square a real number, you'll get a positive. So right now, we would just say this has no solutions. Maybe it would be better to say this has no real solutions. So what that really means is if we want to look for solutions to that equation, we can't look for the solutions to this equation in the familiar space of real numbers that we're used to. We need to allow for something extra. And that's what I'll try to spend this page motivating. And this idea of like adding some extra numbers to get solutions to more equations isn't so novel. Let's suppose that you only believe in counting numbers, 0, 1, 2, 3, 4, and so on. If you only believe in those numbers, then does the equation x plus 2 equals 1 have a solution? No, if you only believe in counting numbers, then it would be a number that when you add 2 to it, you get 1. But if 0 is the smallest number, when you add 2 to 0, you'll get 2. There's no way to get 1. So unless you allow for negative numbers, this has no solutions. Instead, if you want to solve this, you have to believe in a negative sign. You have to say, well, it makes sense to think about numbers that are less than 0. You need to think about integers. But if you're only allowed to think about integers, those are the only numbers you believe in, then does the equation 2x equals 1 have a solution? No, if you only believe in integers, then 2 times an integer would be even. But 1 isn't even. So that has no solutions if you only believe in integers. So you need to allow for more numbers than that. What's the solution to 2x equals 1? A half. So you need to believe in things that look like 1 over 2. You need ratios. The solution to this is a rational number. Which are called rational numbers because they're ratios of numbers that you know. All right, keep on going. If you only believe in rational numbers, then does x squared equals 2 have a solution? Well, what are the solutions to x squared equals 2? plus or minus the square root of 2. So you'll somehow need like x equal to plus or minus square root of 2. Is the square root of 2 a rational number? It isn't. How many people have ever seen like the reason square root of 2 isn't rational? Oh, okay, good. If you want to see the reason, the proof that the square root of 2 cannot be written as a rational number, see an extra credit posted for the course webpage today. There are 2 extra credits posted for today. That's one of them. So this has no rational solution. But the square root of 2, that's like 1.7 something. So you can certainly write down a decimal expansion. That's exactly what real numbers are. They're things that have decimal expansions. This number, the solution to this equation is a real number. So you keep on building up these bigger and bigger sets of numbers to solve more and more equations because, well, you want to know what the solutions are. Does the equation x squared equals -1 have a solution if you're only allowed to look in real numbers? No. The square of any real number is positive. Instead, I would call the solution to that equation complex. Maybe you would ought to say imaginary, both would be correct, but I want to emphasize that I'm building complex numbers. So, let's say what these complex numbers are. So somehow the complex numbers are what you get if you take the real numbers and say, well, I want there to be a solution to x squared equals -1. So I'll just invent a new symbol. I'll call it the imaginary unit, I. And I'll say that this number, I, has the property that when you square it, it gives you -1. So I'm just going to take the real numbers and add to them an extra bonus number. Yeah.
Could you hold up a little bit?
Oh, yeah. Thank you. So what am I going to do? I'm going to take the real numbers and I'm going to introduce some new number, I. So I'll call I also the square root of -1. That is, I is equal to the square root of -1. And, well, I want anything that can be written if I allow real numbers and then also this complex number, I. So I should be able to like add them together, right? So if I take a purely real thing and a thing that's been multiplied by I, that should still be a number. So that motivates this definition. A complex number is anything that can be written as A plus B times I, where A and B are real numbers. So for example, 3 plus 7i is a complex number. Pi minus the square root of 2 times I is a complex number. That make sense? So I'll make up particular terms for some of these. If b equals 0, then a plus bi, well, if b is 0, that's just going to drop out. So that'll just give you a. Well, we already have a word for that. A was already a real number. If a is equal to 0, then a plus bi is a multiple of I. I will call anything that's a multiple of this imaginary unit an imaginary number. That seem pretty okay? So, as an aside, you can still visualize complex numbers. You just won't be visualizing them on a line. Instead, what you'll do is you'll picture them on a plane. You'll picture the real number sitting on the horizontal axis. You'll picture the imaginary numbers as sitting on an axis perpendicular to that. And then you'll just read off a plus bi as the point a comma b. So if you go 1, 2, 3 to the left and up by 1, I would call that point 3 plus I. That makes sense? So you can still visualize all this stuff. You just have to have an extra dimension to visualize it. And let's see, these are numbers. What sort of things should I be able to do with numbers? If I have two numbers, I should be able to add them together. I should be able to subtract them, multiply them, and divide them. So let's just check that we can do those things with complex numbers. Addition and subtraction will be pretty straightforward. Multiplication will be reasonably clear. Division will require a bit of a trick. So, the next page, I'll just talk about the algebra that you can do on complex numbers. So what do you think? A plus bi plus c plus di. What would you want the sum of that to be? If you were to write it as a real part plus an imaginary part. I should be able to commute things around. So you should be able to write that as real parts added together plus imaginary parts added together. That's how you add complex numbers. I will define addition of complex numbers to be a plus c in the real direction plus b plus d in the imaginary direction. Similarly, I'll subtract by just subtracting. How do you feel about that? That seem okay? Let's think about how to multiply numbers, and maybe I'll even just start by multiplying via an example, and we'll just think about foiling. So let's do this bit. Let's multiply 4 plus 3i times 2 minus 2i by just thinking about expanding that out the same way as you would if it were like a degree 1 polynomial times a degree 1 polynomial. I'll FOIL it. So if you do that, I guess you'll get 4 times 2 plus 4 minus 2i, so that's minus 4 times 2i, plus 3 times 2i, plus 3i minus 2i. So I guess I'll do some of the multiplication all at once. Minus 6, I times I will be I squared. That seem pretty okay so far? All I've done is FOILed. So let's simplify some things. 4 times 2 is 8. Negative 8i plus 6i, that leaves me with negative 2i. Minus 6 times, I see an I squared, but what's the whole point of I? What is I squared supposed to be? Negative 1. And then you see some negatives that'll cancel. So I'll end up with 8 plus 6, so that's 14. Minus 2i. That seem reasonable? So we can do that in full generality, and either you can remember just FOIL, or let's actually expand it out and see what generic formula we get. If I multiply together a plus bi and c plus di, so let's see, I think that I'll walk mostly in blue pen, and then I'll write a final value in red. So it'll be ac. Oh, yeah. Multiplying these two things together, I'll get AC first, outside, plus ADI, plus BCI, plus BDI squared. And what is I squared? So it'll be B times D times negative 1, so it'll be minus BD. And now let's just simplify it out. Let's put the real parts together and the complex parts together and see what we get. So I'll see AC minus BD plus the complex part, AD plus BC times I. That makes sense? Oh, and there's the final formula. So if you want to multiply some things together, just remember that I squared is negative 1 and then FOIL. Let's maybe do one last example. Well, how do people feel about addition? People want to see one explicit addition of complex numbers example? Okay, seeing no demand. Let's go down here. Let's try to raise something to the 4th power. And the answer will actually be I think, an interesting and surprising one. Let's compute 1 plus I raised to the 4th. So what does it mean to raise something to the 4th? Multiply by itself 4 times. So let's do that. Let's compute 1 plus I times 1 plus I times 1 plus I times 1 plus I. And maybe I'll even group these together. I'll multiply those two together, and then I'll multiply those two together and see what I get. So, by FOILing, let's compute 1 plus I times 1 plus I first. We have instructions that say how to do that. So that should be 1 times 1 is 1, plus I, so that's plus 2I, plus I times I, so that's plus negative 1. And then do I even need to do the formal expansion for the second bit, or do I already know what it'll be? I already know what it'll be. So let's just do a bit of simplification. 1 minus 1, those cancel. So the second bit will just be 2I. So I end up with 2I times 2I. Guess that's also known as 2 times 2, which is 4 times negative 1. Oh, cool. So I took this number, I raised it to the 4th power, and I got negative. So what do you think? If I just produced a 4th root of negative 4? Yeah. I mean, I may have lucked into it, but. So here's an observation. 1 plus I is a 4th root to negative 4. Any questions just about that? Cool. So we can add, and we can subtract, and we can multiply. We still need to figure out how to divide. And in order to divide, well, it would be easy to divide if I were only allowed to divide by a real number. So then I would say, well, if I took 3 plus I and divided it by 2, that would just be 3 over 2 plus 1 over 2I. I could distribute. But what if I divide by a complex number? Then it gets dicier. Then I need to think of a trick. And here's the trick. The conjugate. So the complex conjugate of any number, a plus ib, so that's a plus ib, and I'll draw a little line on top of it. By that, I will mean a minus ib. And that's just a definition. Whenever I say a plus ib and I draw a line on top of it, I just mean take the complex part and stick a negative sign in front. So let's see an example of this being used. Let's compute the product of 4 plus 3i times the complex conjugate of 4 plus 3i. So I guess that will be 4 plus 3i times 4 minus 3i. Because that's all the conjugate means. The conjugate means take the imaginary column and make it negative. What do you get when you multiply those two things together? Well, I guess maybe I'll ask. How many people want to see another example of complex multiplication? Okay. I'll talk through it. Those of you who have already done that multiplication, what did you get? Yeah, but say it louder. You said it, right? Oh, okay. Well, then your sneeze sounded a lot like the correct answer. So let's compute this. So how do we multiply? Well, we can either memorize that formula, but that seems too hard, so I'll just FOIL it out. So that will be 4 times 4 is 16. 4 times negative 3, that's minus 12i. Plus 3 times 4, that's 12i. 3 times negative 3, minus 9i squared, so that's minus 9 times negative 1. Do you see anything that cancels in that? What cancels? 12i. Oh, so that's handy. There's no more complex bit. And I guess another thing that cancels is I see a negative times a negative. So that'll become positive 9. And I wind up with 16 plus 9, which is 25, I guess. So here's the thing to remark on. That number 25, does it have a complex part anymore? So this is a real number. In general, whenever you see a complex number and you really, really wish it were not a complex number, you wish it were real, you can make it be real by multiplying by its complex conjugate. And, well, in general, I guess one option is, well, what do you think? Could we do that in complete, just whenever we wanted for any complex number? Yeah, and something very similar would happen. If you were to FOIL it out in the same way, would you still get imaginary part canceling? Yeah, I think so. Well, maybe I'll jump to just the answer first. A plus bi times the complex conjugate of a plus bi will always work out to be a squared plus b squared, the real part squared plus the purely imaginary part squared. How many people want to see it FOILed out in detail? Okay, good. I mean, you can, right? So the important fact is if you multiply a number by its conjugate, you'll always get something that's real. Even if you don't remember this fact, that you always get a squared plus b squared, remember that you always get something real, because that will motivate the following choice. So let's suppose you want to compute a quotient. Let's compute the quotient of 1 plus I divided by 3 minus 2i. And the eventual goal is I want a complex number. I want something that looks like a plus ib. And that would be easy to do if I were dividing by a real number, but I'm not. But what could I multiply that denominator by in order to get a real number? What's something that I can multiply any complex number by to always get a real number? It's conjugate. So if I could multiply that denominator by its conjugate, I would get something real. If I multiply the denominator by a number, then what should I do with the numerator? Same thing, multiply it by that same thing. Oh, neat, so that's like an algorithm. Let's do that, and then let's just go through the motions and see what we get. So let's compute 1 plus I divided by 3 minus 2i. We'll multiply and divide by the complex conjugate of 3 minus 2i, which is, of course, just 3 plus 2i. So let's multiply and divide by 3 plus 2i. Right, that doesn't change the fraction because I multiply and divided by the same thing. And now let's just expand out the numerator and the denominator. The numerator, I don't know what it'll be in advance. The denominator, I know it will be real. Let's FOIL these things out and just see what we get. I guess I'll FOIL out the denominator, and then I'll give you guys a moment to do the same work in the numerator. So in the denominator, it looks like I get 3 minus 2i times 3 plus 2i. On the one hand, I could use the formula that I know it'll be a squared plus b squared, but I think I actually want to go through the motions. 3 times 3 is 9, plus 6i, minus 6i, minus 2 times 2, that's minus 4 times I squared, so plus 4. So in the denominator of this fraction, I see 9 plus 4, well, that's 13. What about the numerator? What do you get when you FOIL out the numerator? Sorry, no, I shouldn't phrase that as a question. FOIL out the numerator for me, I don't want it.
Plus 2i plus 3i plus
2y squared.
Nice. And let's just look at that last term. 2 times I squared is the same thing as minus 2. So you take that and you simplify it, and what do you get? Just in the numerator, what is the just real part of the numerator? 1. It'll be 3 minus 2. And what is the imaginary part going to be? 5i. 1 plus 5i. By FOILing and simplifying a little bit. The last thing that maybe we should do is I want to write this as a plus a real number plus a purely imaginary number. And now that I'm just dividing by 13, that's easy to do, right? I'll just distribute the division. So what should I wind up with? I guess it will be 1 over 13 plus 5 over 13 times I. That makes sense? So instead of giving you a formula for division, similar to the formula for multiplication, it would just be too big to remember. Instead, you should just remember the technique. If you want to compute a fraction where the denominator is complex, you should multiply the denominator by whatever you need to turn the denominator into a simpler thing. That's generally a process called rationalizing the denominator. And, well, I think that I want you guys to do the next example on your own. So take a moment, compare with those around you. Compute for me 4 minus I divided by 3 plus I. Good, and everyone is doing. You guys could absolutely consult with each other. Oh, I mean, ask me questions.
So is the 3 plus I the conjugate already, or is the 3 minus 2i?
So you need to, right, so you want to multiply and divide by something.
Right.
It should be the same something. And it should be the something that you need to divide by to make the denominator real.
So it would be 3 minus 2i, the conjugate already?
Except no 2.
Oh.
Yeah. But yeah, otherwise.
it's a negative I squared, so it's negative and then parentheses.
Oh.
Cool. How do we feel? What is this? What is 4 minus I divided by 3 plus I? Yeah.
11 over 10 minus 7 I over 10.
Is that what you said?
Yeah.
Okay, cool. Is that a consensus answer as well? Anyone get something different? Anyone want me to talk through it? Okay, cool. Yeah, right, so if you want to divide complex numbers, there's an algorithm. Do you think that this algorithm has probably been implemented on machine at some point? I can't speak for whether or not your handheld machines understand complex numbers, but if, say, when you're doing the homework and you do a computation and you want to check it, well, one way to check it is by literally having a machine do it. That agree with the answer? Nice. So at the very least, if our computation is wrong, then so is Wolfram's. Sorry, I said our computation, but I didn't contribute at all. If your computation is wrong, then so is Wolfram's. So, if you like the content that we just hit, is a little bit of the back of the book appendix content. Just what is the algebra of the complex numbers? But what's the point of the complex numbers? Why do we care? We care because they're the places where we can solve quadratic equations. In fact, they're the places that we can solve any polynomial equation. But right now we're only interested in quadratics. So, in fact, if we wanted to write down, well, any number has a square, any real number now has a square root. Because any real number is either already positive, in which case it has a square root that's real, or it's negative, in which case we can pull out the negative 1. If I want to take the square root of negative 5, I would say, well, that's the square root of negative 1 times 5, which is negative 1 times the square root of 5, which is I times 5. I times the square root of 5. So I've just formally constructed these new numbers, which are square roots of negatives. If I wanted to take the square root of negative 100, well, what is the square root of negative 100 then? Yeah, I would say it that way. It should be like 10i. And you'll notice I thought the completing the square technique, or when using the quadratic formula, the only bad thing that can happen is a negative might show up inside of your square root. But now we're just fine with that. A negative shows up inside of a square root. That thing is just imaginary. And we'll just deal with it. It's imaginary. If we want to find the solutions to this using, I don't know, the quadratic formula, let's use the technique from the front page. Right? We did it by completing the square. So we rewrote that as x plus 1 quantity squared plus 1 equals 0. So x plus 1 quantity squared equals negative 1. And let's move that square to the other side, because now I can take the square root of a negative. I'll get x plus 1 equals plus or minus the square root of negative 1, also known as plus or minus I. Now can I easily solve for x? What do I still need to do? Just subtract 1. So I can solve quadratic equations, all of them. I just have to be willing to accept that sometimes the solutions won't be real. I think that I'll point one thing out. So I've invented these new numbers, these new complex numbers. And I've shown that you can take the square root of any real number now and get a complex number. What if I take the square root of a complex number? Is it so clear what that is by what we've done? Say louder.
Like negative and square root.
Worse than that. What if I try to ask you to take the square root of That's more ambiguous. It's not so clear what to do there. Extra credit announcement. There is a formula in general for the square root of any complex number in terms of square roots of real numbers. And an extra credit posted for today will walk you through it. You can compute the square root of 6 minus 8i, and doing so is an extra credit. In general, you can compute any square root. That's really what the extra credit is, not just doing it full. Cool. So in general, right, now you can just use a quadratic formula. You can solve any quadratic equation, because now we can take square roots of anything. If you want to solve x squared plus bx plus c, you know what the solution should be. It should be x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And this thing inside of the square root, it may be negative, but that's fine now. The answers will just be complex. That makes sense? So we've invented these new numbers, and these new numbers are where solutions to quadratic equations may live. And let's focus in on that thing inside of the square root that somehow like determines the behavior of the solutions. So it's a special case of a more general algebraic doodad called the discriminant. The discriminant of the polynomial ax squared plus bx plus c is this thing inside of the square root. And it's called the discriminant because it discriminates between the different types of behaviors the solutions might have. For instance, let's suppose you compute the discriminant and you get that it is positive. So if the discriminant is positive, if that thing inside of the square root is positive, well then how many distinct solutions will this quadratic equation have? Is positive. So there will be a plus or minus, right? So if you take a real number and add or subtract a real number and then divide by 2, how many possibilities are there? 2. You could add or you could subtract. So in the case that the discriminant is positive, this polynomial has 2 solutions. And, well, if the discriminant is positive, is this square root term going to be real or complex? It'll be real. Every real number is also complex, but it'll be a real number. And then I'll see a real number plus or minus a real number all over 2a. Will that be real? Yeah. If the discriminant is exactly equal to 0, so if this thing inside of the square root is 0, let's just try to read off the solution. What's the square root of 0? 0. What's negative b plus or minus 0? Negative b. So it doesn't matter if I add or subtract, does it? So if the discriminant is 0, how many different solutions are there? Just the one. And that solution, is it real or complex? Real. I'm assuming a, b, and c are all real numbers right now, which is real. Finally, if the discriminant is negative, well, then let's read it off. If the discriminant is negative, then the square root term, will it be real or imaginary? Imaginary. So I'll see a real number plus or minus an imaginary number all over 2a. And it still matters if I add or subtract, right? Okay, different things. So how many solutions will there be? which are, in this case, complex. Moreover, these two solutions are related to each other. All right, the two of them will be, all right, negative b over 2a plus a number times I, and that'll be negative b over 2a minus a number times I. These two quantities, how are they related? What's the relationship between them? I guess what's the only thing that's different is whether or not the imaginary term is positive or negative. What's the word for when you change your complex number by making the imaginary term negative? It's the conjugate. Whenever you see a quadratic equation, if it has complex solutions, they'll be really closely related to each other. They'll just be complex conjugates. Oh. Sorry. That was already written. I should read what's in the notes before I start to make my next point. That makes sense? So that's a neat observation. That means that if I give you a quadratic equation and you compute the solutions and you get two complex numbers, what do you get if you multiply those two solutions together? What type of number? Something real. That's exciting. So, maybe I'll remind you here, the discriminant equal to delta is given by the thing inside of the square root. So that is b squared minus 4ac. And the discriminant is also, the letter delta is often used for it. There's nothing magical about using the letter delta. I will. So, without finding any solutions, let's try to answer some questions about some polynomials. Without actually finding them, let's count how many solutions that polynomial has, and we'll even say what type of solutions they are. And we'll do it by computing the discriminant. So let's compute the discriminant. So the discriminant, delta, is equal to b squared, negative 4 squared, minus 4 times a times c. And let's just see what we get. So I guess that's, this negative inside of the parentheses doesn't matter. It gets squared away anyhow. So that's 16 minus 4 times 3 is 12 times 2 is 24. Is that positive or negative?
Negative.
Negative. Maybe it's even negative 8, but I don't care that it's negative 8. I just care that it's negative. The discriminant is negative, so how many solutions does this equation have? Are they real or complex? Complex. They're even conjugates of each other, but this question doesn't ask that. So this has two complex solutions. Here are 3 remaining things to compute. So I think I'm going to have you guys break up into 2 groups and do 2 of them, and then we'll do the last one together. So 3x squared minus 4x plus 2. That's the same one again, isn't it? Yeah, okay, so that one's the same one. Copy paste error. X squared minus 4x plus 4. X squared minus 4x minus 4. Compute the discriminant. So the discriminant is 0. So how many solutions are there? Is it real or complex? 4x squared minus 4x minus 4. The discriminant is positive. Maybe you computed that it was 10, I guess? Or whatever it was positive, don't care. The discriminant is positive, so how many solutions will there be? Will they be real or complex?
I didn't go that far.
Yeah, like something like that.
2 words can go that far.
My 11 a.m. got one so I knew that one more up was